We just got a question from chat, and the chat asked, how is gold made? Do you guys know how gold is made? Just gold. Gold in general. Fool's gold is actually made different. Yeah, it's pyrite, chalcopyrite, and iron pyrite. Anyway, okay, so this is actually super cool. This is how gold is made, and actually this is how almost every element in the universe is made, okay? So we start off, universe is super hot, right? Universe is filled with gas. The majority of the gas in the universe just out there floating is hydrogen gas, okay? Just super simply, most of our nebulas and all that kind of stuff is made with hydrogen gas, okay? When you get a whole bunch of hydrogen gas that floats around each other, it gets pulled together because atoms attract atoms just through to like microgravities, and you turn it into a sun. Okay, and it starts off as a very small sun, and as the sun gains more and more gas, the molecules are bouncing around because they're gases. Molecules bounce around, and as you get more and more of them,
I know what it's called.
Yeah, we're getting there. So it's got nuclear fission.
Supernova, right?
Yeah, we're gonna get there, but it's a very specific way gold's made. So the hydrogens are gonna bounce around, and they're gonna fuse together once they bounce around hard enough, and they hit, and they make a helium. Okay, so now you have heliums bouncing around, okay? And now we're gonna work in twos, right? So it goes hydrogen, helium. The next thing that's gonna be made, we're gonna skip lithium, and it's gonna make beryllium, okay? So now you have hydrogens, heliums, and berylliums bouncing around. Berylliums are going to bounce around and run into the hydrogens because there's more hydrogens. So we go hydrogen, helium, lithium, beryllium. The next thing is made is carbon, is number 6. So now you have carbons, berylliums, heliums, and hydrogens bouncing around. Now you're going to ask, okay, well, how do we make the lithiums and the stuff in between? Hydrogens are going to bounce into the carbons, they're going to bounce stuff, but it's going to make less of them, okay? So whenever we have a molecule with a divisible by 2 protons, there's going to be a higher amount, and whenever you have them not divisible by 2, there's going to be a lower amount, okay? So now we're at hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, basically anything, so there's going to be more oxygens, anything with 2. That reaction keeps going until we hit iron. Okay, once we hit iron, okay, this is as big as you can possibly get an atom through standard nuclear fission. And if you're looking at a sun, as you get more and more iron inside a sun, the sun starts turning red. Okay, this is what we start calling those red supergiants, right? That's why they're red, because they're just filling up more and more iron. And so whenever you start getting iron, right? Iron is the heaviest element in there, and it's a metal. That iron starts making its way straight to the core, right? It's going to go to the point of lowest gravity, right? It's going to go right to the core, right? And you start amassing this big ball of iron, and this is not metal iron. This is gas iron in the middle of it. And it's getting bigger and bigger and bigger, and eventually that iron gets so big that its gravitational pull on the rest of the gases is stronger than their repulsion of being a gas, and they all collapse in on each other. And instantaneously, in just a quarter of a second, when everything collapses in upon itself, you make every other element in the universe in that microsection. It comes in, and then it explodes out, because when you make all those elements at once, now their ability to repulse each other is stronger than the iron's ability to hold it, and it all explodes out in like a massive supernova explosion. And that's where you get your gold and irons and all that kind of stuff. And then when it explodes out, we get another cool effect. The heavier elements, right? So you get like your uraniums and your heavy like metal stuff, that, right? They don't go as far, okay? When they explode, they slow down. They're able to slow down their inertia. They basically like it's not friction, they just slow down further. So when you build planets out of these elements later, you're gonna notice that the planets closer to the center of the explosion are gonna be your stony planets, like our Mercury and our Venus, okay? And then when you get super far away from the initial explosion, you're gonna get gas planets, like our Jupiters or Uranus and stuff like that. And you can actually track back where the explosion of the supernova happened, and planets that are closer to the explosion are going to be more rich in those heavy elements such as uranium. So if we ever go to Mercury and Venus, and we've actually sent probes there, stuff like that, we're going to find that there's a lot more nuclear like uranium, plutonium, stuff like that than we do on our Earth. And it's the exact same reason why places like Uranus and like those planets out there are a lot more gaseous than our planet.
Every element that we have here was made back there
on an instantaneous
explosions.
Yeah, an instantaneous explosion. And then when that thing explodes, Yeah, and then when it explodes out, all those heavier elements, right, they start collapsing onto each other, and then they start making small asteroids. And those asteroids then start smashing into each other, and they make planetoids. And when those planetoids start smashing into each other, they start making planets. And every single time they smash into each other, they get superheated because this like massive giant rock hitting massive giant rock. They basically like melt into each other, and when they melt into each other, all their heavy iron cores go into the center. So like our planet Earth, right? It has a core, right? And that core gives us a magnetic field that protects us from radiation, right? Well, our core is actually oversized. Yeah, our core is actually oversized for our planet size. Like we have a much bigger core than what we naturally should have. And the reason for that is that our moon that we have smashed into us, deposited its iron core into us, and then it accidentally got whipped off instead of fully combining with us. So our moon doesn't really have much of an iron core whatsoever. It has a super teeny tiny one, and we have an oversized one, which allowed us to be protected. Yeah, science facts.
Yeah, the moon's a Chad.
Right? And the moon protects us from like meteors and shit. Yeah, it makes the waves. Also, did you know that the moon, because it doesn't have a protective field, it's been hit with so much radiation that it actually has a whole bunch of what's known as hydrogen 3+ up in there, which is going to be really good for nuclear fission. So there's a huge incentive for companies to like mine the moon dust because it's very, very high in what's known as deuterium, and deuterium is very, very good for nuclear fission, not nuclear fission, not fusion. Sorry, fusion, not fission. Fusion. So fission is splitting.
Okay.
It's very good for the fusion. Yes. So then what you call it?
It's the harder one to do, right?
Yes, exactly. Which is why deuterium is very necessary, and the moon is covered with it. Absolutely covered with it. The only way you get deuterium naturally right now, and by I say naturally, is from nuclear power plants. When they break it apart, enough radiation comes out and they cool it down with water, and that water turns into deuterium. That's the only main way of them getting it right now. It's known as heavy water. Exactly. Exactly. We got a really good question from the chat. It says, would fusion reactors completely deplete Earth's hydrogen? No. So you can't fuse hydrogen, okay? You can fuse deuterium, which is it's a neutron infused hydrogen. So like on Earth, 99.999% of all hydrogen is hydrogen just normal, okay? It's just hydrogen like 1, okay? But deuterium is hydrogen 2, okay? And that it decays like within seconds normally. But like when you're in a place like the moon where it's just constantly been bombarded by radiation, and there's no ability for, it's so cold it has no ability to actually jump down into its lower form, it's just covered in deuterium. And deuterium is very, very good for a nuclear fission. It's easier. Any other questions, Shad? I didn't expect this to turn into a science lesson, but I'm chill with it. Sorry, do you think we'll ever make a sun? Did you ask, do you think we'd ever make a sun? Is that a question?
Yeah.
Okay.
Kind of like the reaction to it. I know we've been working on it, but like, that'd be amazing.
So,
Extremely difficult. I zoned out with this one.
so the question is, can we make a sun? And the thing is, the amount of material we would have to collect, like a sun is a self-perpetuating reaction as soon as you get enough material, okay? Like as soon as you collect enough space, like gases together in one place, it will make a sun, okay? But like the hard part is like putting all those things together, because like when you're in space, there is like no air, like it's a vacuum, right? So how are you going to move gases effectively to make a sun? And what would be the point of effectively moving those gases to make sun? If you could effectively move all those gases to a point to make a sun, why wouldn't you just harvest those gases for things that we could use instead? Like, I'm trying to understand what the point of making a sun would be.